get started here. The first thing we'll do is our presentations. These are the two student winners of the Connecticut Science Fair ASGH Charles Hammond Science Award rather. And I'm going to go ahead and turn it over to Scott Tracy and Bill Denaya. I don't know if Bill's on.
Yes, he is.
Okay, terrific.
I saw him.
So you guys can go ahead and introduce our winners, and we'll go from there.
Okay.
Thank you.
Many of you understand that when we do this every year, we just remind ourselves of what this activity is about, why the ASGH does it, why it has the name it has. I don't have the date when we started judging at the science fairs, probably 30 years ago. I'm going to guess 1990. Former president and club member and mirror maker extraordinaire Bob Royce came up with this idea that since Connecticut has this great science fair from which winners of the science fair awards go on to a national science fair. This year it was in Atlanta. Bob felt that we should be giving people who do astronomy projects some recognition or special recognition to encourage astronomy and physics. And so for the past 15 years, ASGH members Alan Hall, Carl Williams, and I got together at Quinnipiac to judge astronomy related projects. This year, Bill Denaya joined us, and I am enormously grateful for that because the other gentlemen mentioned are no longer available to do this. And since we have different skill sets and the astronomy projects are at different levels, we need each other's strengths just to make sense out of many of these, at least in the current time. I should mention that for at least for most of those past years, we were sometimes lucky if we found anyone who did anything in astronomy. Sometimes we had to step out and say, well, look, we got kids here that they deserve recognition. And so we would find something related to astronomy. We had one, a really cool laser project years ago and some other applications. But I'm saying this because I don't know if it was COVID or what, for the past couple of years, we've had over 10 very good entries into the science fair in astronomy related topics. And so it gets to a point where it's almost painful to try to, separate folks out into which one, who. I'd like to give out a lot more awards, but then again, this keeps things really special. Now, when one of our founding fathers, mentors, leaders, and inspirers, Charles Hammond, when he passed away, it was quickly decided that we should, since he was so much into promoting astronomy, it makes sense to name this award after him. Those of us who knew Charlie knew a fellow who he eventually retired as chief science librarian for Emhart Corporation and had access to all kinds of resources. He built his observatory in East Hartland, which was more like a complex than an observatory, and it was a big deal to get up and see what he has. Charlie inspired us, those of us who built observatories. Most of us copied his design. Certainly Phil Dabrowski did. I think I could say that of Greg Vinci and others. And so it's nice to have this opportunity to think about Charlie at a minimum once a year. So
it helps memorialize him.
Yeah, I just wanted to make sure I didn't leave anything out because Charlie contributed so much to our club. But so anyway, that's how this has evolved. The way it was designed was there would be a senior winner and a middle school winner. as we had less and less middle school entries, or seldom had one, we decided last year and again this year to award 2 prizes, but to 2 seniors. And so with that, I'm going to turn this over to Bill so that he can introduce our first of our 2 recipients.
Well, that's a surprise because last we talked, you said you were going to go first, but that's fine.
I can do that if you
You
want.
can go first.
Yeah.
You just open the talk. But let me just add one more thing, that the immortalization of Charlie Hammond does continue through the next generation. His son Bob is here with us tonight as well.
Yes.
Excellent. Excellent. This, I'll tell you, the experience of reading and comparing the science fair projects that, along with Scott, was inspiring. The level of work really pushed my personal thresholds of understanding of our science and our hobby, and I learned a lot by doing the process. And so our first speaker will be is a senior, a graduating senior, and Sam is been accepted to Rochester Institute of Technology, computer engineering department. Is that correct, Sam? And he did his topic on using a camera to identify the celestial pole. For those of us that do astrophotography using I lost the word, but we have to get focused in on that, on the celestial pole oriented, so that we can track the stars or stellar objects that we're trying to take lengthy pictures of without getting
Bill, can I interrupt for a second? President Markovich, would you please close your PowerPoint? Chris?
You want me to stop sharing?
Yes, please.
Okay. All right.
There we go.
There we go. So, Sam, as I understand, and I will tell us the whole story, Sam, undertook the project self-directed, and then his science teacher discovered that he was doing it, and coached him into competing at the science fair. So that's awesome. And I hope you go at some point commercial with your project, because I want to use it. So that's let's listen to what Sam did and let him tell us his story, and then I think we'll hold for questions towards the end. Or how would you like to do it, Sam?
Actually, first off, how long about should it be? Because I have a lot, but I don't know how long you have.
Yeah. No.
Somewhere between 20 minutes and half an hour. My guess is you're going to at least go for the half an hour.
Yeah, I was.
We hate to cut folks off. It's always a balance. Let's keep going because we love the topic, but we have another speaker too.
Yeah.
Or 2 speakers. So let's see how it goes, Sam. I'm sure it'll go fine.
Let me share my screen
while he's speaking, please.
Yes.
I'm just trying to share my screen. This. All right, so you can see presentation now.
Yes, sir.
All right, cool. So I guess this has to really start from the very beginning of my getting into astrophotography, because really my senior year project has been, or my interest in astrophotography has been a culminating interest over like the past 3 years. And it started just by me and my dad taking bird photography, bird pictures. And that's what gave us, that's how we had cameras in our household. And I always loved going out on expeditions with them. But that's basically where I got my cameras from. And my love for space has always been with me. And so I had the idea, let me try to take this camera and take a tripod and go take pictures outside. And so I went outside with the Nikon camera that we had. It was a 400 millimeter zoom, so it can get pretty close into the sky. And I tried to find Andromeda, and I was able to find it. Now, unfortunately, I'm kind of in the process of moving, and so I don't have my main computer with me, so a lot of my pictures are stuck on that, and I can't get to them. But basically, you can imagine taking a single picture of like 1/10 of a second at the sky is going to be very blurry and very hard to distinguish. But the very essence of it was I was able to see the galaxy, and that was like this. It was really the the starting point of my desire to learn more about this stuff. But what I learned from this was there's a really big issue with the movement of stars with the Earth's rotation that you have to counter, and also gathering light. Those are the main two things. So the first challenge I wanted to overcome was taking longer exposures than a couple seconds, because at certain zoom lengths, the stars are going to move, and so you need to move the camera with them, with a star tracker or one of those fancy celestial mounts or whatever. So my first attempt was a barn door star tracker. This was made in like the winter of my sophomore year, about just based on wanting to take pictures of the sky, knowing I had a camera to do it, but wanted to use anything else I had. And so I went to the wood shop with my dad, and we put together a little opening mount. I took a stepper motor and I controlled it with an Arduino, a little microprocessor, and I programmed it so that it spun the threaded rod at exactly the right rate to open the doors at the celestial rate, so that way it would perfectly counter the stars. Now, naturally, with any project, there's a lot of hoops to jump over. And so one of the main issues was proving that the tracking rate was accurate, because I can do all the calculations I want, but if it doesn't work in the real world, I got to figure out why it's not working. So one of the things I did is I took a laser pointer and I put it on the top of the surface of the top barn door down in my basement, and I opened it over a period of time and like measured it across the whole downstairs, how far it went up, to try to calculate that. Hold on, my monitor's disconnected. My monitor is screwed. All right. Is it still sharing?
Yeah.
I think it's still sharing. Okay, cool. All right, so there's many issues I had to overcome with that. But over the way, I was learning about polar alignment requirements, and I was learning about noise requirements. I was learning about all this different stuff. But the most impending issue was the coupling between the threaded rod and the stepper motor, because at the sheer angle of the mount of the barn door tracker, of like the top barn door and the bottom barn door, and the weight of the camera, there's a lot of shear force on that threaded rod, and the coupling between the threaded rod and the stepper motor wasn't strong enough, and it would start to like bend and twist the mount. And so as it was spinning, it would get a sort of wobble in it. And I think where is it? This image right here, you can see like there's slight streaks. This was a 10-minute image, by the way. And it's cropped in a lot, but there's also, this is the only picture I had, it's a very slight like spinning motion. And this was wobbling, and I could not overcome this because I didn't have anything else to try, any other better coupling mounts. So at this point, after trying so many different things, I decided it was worth it to invest in a tracking mount and see what else I could do with my my ingenuity. But this was one of my best pictures from the barn door era of Orion, with a 10-minute exposure that I didn't even expect to get anything good out of, and it ended up having a lot of color because Orion is so forgiving. So I got my hands on a star tracking mount, the Fornax Light Track 2, which is a pretty high-end tracking mount for the tracking mounts, not getting into the full-blown telescope mounts. But my compromise was I was not going to buy a polar alignment camera. They sell like the QHC Polemaster, or they sell polar scopes. And I wasn't going to get one of those because that would be even more expensive on top of this expensive mount. And what I was figuring was a Polemaster is just a camera with a program attached to it. And all it does is it looks up at the sky with the camera, and the program does all the thinking to align them out. So I could use my own camera and do the polar alignment procedure. And so that was basically the start of my junior year, kind of in the summer before it too, of deciding I'm going to write a program to align this fancy mount, so that way I can then use that camera to take pictures. And so I programmed the main interface in C++, or no, sorry, I programmed the main interface in Java. And then in order to interface with my camera, I had to use C++ because the camera makers provided kind of a driver thing that I could use for C++. So the first issue to overcome was, how do I get images from the camera to the computer? And I did this by transferring the live view images over a socket connection between the programs. So basically just connecting, because two programs run separately on your computer. So I need to bridge that gap with a socket connection, which is basically sending over the internet like you would stream a video. But the main challenge was getting it fast, because if you're trying to move the mount to align at a tiny little point and you bump it a little bit and that point shoots off your screen and you see it 2 seconds later, it's going to be really difficult. So I had to make sure that was very low latency, and I went into figuring that out as part of my part of the procedure. But the main point of this program was to polar align. So I needed a procedure of how do I polar align the mount. And the main procedure used by like the Polemaster program was, first you locate the mount's axis on the camera frame, and then you use the stars to find out where the north celestial pole is. That's the mount's rotational axis. And then you align the two. So there's 3 main steps. So the first step was calculating the mount's axis. And the main procedure for this was to use the, you take 3 separate images at 3 different points of rotation around the tracking mount. So you won't rotate the mount all the way one way, in the center, and then all the way on the other side, while the camera is stationary on top of it. So basically what you end up with is the same star, Polaris in this case, in 3 separate coordinate positions around the rotation of the mount. And what you do with this is you then calculate where those rotate around. And that's the basics of getting the center of rotation. So that was the first step. And now the second step, I'm hoping I can shift tabs here because pictures are in my document. Do you see it if I switch to like this tab? Can you see the new image?
Yes.
All right, cool. So what is this? So the second step was to calculate the rotation of, to calculate the location of the north celestial pole. Now, it's an invisible point in the sky. And so to calculate it, you have to use the location of nearby stars. And you could do this by plate solving. You could do this by seeing the rotation of the stars over time. Because like if you just pointed at the general region and you took like a very long exposure, they'll form streaks around it. And these streaks are all circling around that center point. But how do you calculate that center point? So the way to do this was you do it once where you calculate where Polaris is at 3 points, you get center of rotation, but you have to do that over like 10 minutes or like 15 minutes. So you get your framework of where Polaris is in relation to the center point. And then you get a framework of where a third star is in relation to that point. And so once you have these 3 points, you can develop a similar triangles method. So you have a triangle. So you have an angle and you have 2 side lengths that are constant in relation to each other. So you can scale this however many pixels across the stars are. I guess if you guys have any questions throughout this, it's probably better to jump in because I don't think I'm doing a good job at explaining things. It's all like flooding back to me. I'm not going to think of that at all.
I think
You're doing just fine, Sam.
All right. Thanks. Okay. So that's locating the North Celestial Pole. Now, the final step is to actually align the two. So this is where the live view really comes in. You have to be able to very quickly like see a live update view of where the stars are, but you also have to know where to move the star. So the third step is the program has an overlay. And what it does is it shows you where you have to move Polaris on the camera frame in order to align them out. So as you can see in this frame, you have the original where it is in the first one, that's on the bottom. Like when you first found the mount axis and you first found the celestial pole, that's your unaligned mount. Now to align them out, you have to move Polaris to the new location shown in yellow. And is doing that, the North Celestial Pole will be moved to the mount axis. And you don't want to move the camera on top of the tracker. You want to move the whole tracker because that's moving where it's centered around. So that's the basic layout of how the program works. That was my last year program. However, this was all fine and good working, but the difficult part came in was proving this accuracy and proving that it was actually doing what it should be doing. So I did get some pretty good pictures. There's the Eagle Nebula with pillars of creation deep inside there. And that was actually pretty cool to see that I could actually get a picture that the Hubble had gotten or whatever. And then that's, I think, the Whirlpool Galaxy too. So I got good pictures, but it was very inconsistent because there was many different issues, and I didn't even discuss the star centroiding, which I'll discuss very soon. So all the procedure in general worked. That was the proof of concept of the junior year science fair project, but I really needed to work on making all these algorithms more impactful and more efficient and more accurate. But this whole project was like on my own time over the summer and into the fall. And then the teacher came to me and was like, hey, we have open spaces for the science fair. You want to submit it? And I was like, sure, does this count? And so that's how I ended up submitting it junior year. And that's how I got into being in the science fair. But it was all just my desire to get it working. So yeah, I basically wanted to improve all my calculation methods. So I never got into star centroid. There's a whole rabbit hole that took me a long time to figure out. But basically, on the camera frame, a star appears as a blob of pixels. Now, in order to use a star's point for a calculation, like you need the center point of a star in order to be able to calculate where the 3 points of the star are in the center. You need this center point. This is basically the foundation of finding all of your future calculations. And this has to be really accurate. However, if you just try to average all the pixels to get the center point, the most intense point, you're going to run into issues with noise. All these blue pixels are an artifact of the high intensity light appearing on the camera frame. And this red pixel is an example of a hot pixel, which is like a failed pixel on the camera sensor. And so these are both forms of noise that really have a bad impact on the resulting centroid. And so my senior year was all about optimizing my algorithms. And so instead of trying to average all the pixels to get the center, I switched to trying to fit an equation to all the pixels, because stars form a normal distribution of pixels on the camera frame, which is this kind of curved shape. Think about like a normal curve, but in 3 dimensions. And so this is represented by the Gaussian equation, which is basically that dome, but it can be all lopsided and all stretched, and you have to fit this to the star data. Now, this was like couple months of trial and error and trying to figure out what the heck all this math was, because it was way above whatever I used to be doing. And I don't really think I can explain it well enough to get into it. But basically, that was the premise of improving the centroiding, was being able to fit this equation to all this data. So then the next step. So that was the premise of it. I got a fit equation. But now what I need to do is I need to improve the accuracy of the center of the mount. Where's this one? Here it is. So this is the location of, this is how I was calculating the center of rotation of a star. I have the same star, star A, star B, and star C, that all represents the same physical star, but has 3 different points because I rotated the camera around the mount. But why should I only be using one star? How do I know that this isn't some weird glitched result if I only use one star? My solution was to pick every star in the frame of the image to do this calculation with. The same 3-star calculation, which is the same star just in 3 separate images, but for every star in the image. And this was another difficult challenge to overcome because I had to find all the stars in the image. How does the computer know what a star looks like? So what the very basic version that I employed was first finding all of the most intense pixels. So step 1, you have a blob of pixels. Step 2, you take the most intense pixels of the image and you select them and get rid of all the other pixels. And then the third step is to look in this blob of pixels and say, are these too close to each other? Are they within a certain distance of each other, which would mean they're part of the same star, in which case you get rid of all but one. And then the last step is to run the centroiding algorithm on each of these singular pixels to result in the centroid of each star in the image. And so that was the basic of getting all stars in the image. And from there, I had to calculate where the same star was in each of the 3 images. This is star matching. I got to figure out how to explain this because it took me like so long to try to explain this in the paper. But basically, the user can easily see Polaris in 3 separate images, the brightest star. And so the user has to click on Polaris in each of the 3 rotated images. But how does the computer know what star is what? If it's going to try to take the same star in 3 images and find the center point, it has to know that this star in the first image is the same star in the second image. And so this was the star matching algorithm. And so how this worked was, where is this? Where are you? Here you are. Is that it? No. No. I can find it. Okay,
So while you're looking for this, Sam, can you explain why you didn't use plate solving?
Yeah. So I had toyed around with the idea and I had downloaded one of the simple plate solving things, but my main issue was I didn't understand enough about like, well, one, computer science to incorporate like the plate solving program to like send my image out and then get it back. I didn't really understand that. And it was always in the back of my mind, but I also knew that it can take like a minute to plate solve a single image. And if it's going to take a minute to get feedback on my polar alignment, how am I going to be able to correct this and then retry it again? But I also still have the idea, and I would have tried it if I didn't have to submit my project 3 months ago, to not only prove the accuracy of the polar alignment, like the accuracy of my north celestial pole position calculation. I'd have wanted to prove that with plate solving, and not only prove it with this calculation. Oh, I made a video. That's right. I made a video explaining this, but I'll give you the basic example. So basically, if I click on the same star in 3 images, the computer can calculate a rough estimate of the center that it rotates around. And given that, it can also calculate the angle that the star rotates around it between 2 images. So if it knows this angle, it also knows that this angle is the same for all stars in the image between 2 images. Like both this star, the blue circles, have the same angle between these 2 orange circles. And any 2 first orange circles have the same angle if you form an angle from the center point out. And so it could use this angle to calculate the position of all of the stars. Where's the guess? Yeah, so this is what it would do basically. It would use the angle. The green line is the line between the original star, the first star location, and the guess for the second star, because it's not going to be perfect because the first guess of the center is not perfect. So it's going to use this guess to search for the next star. And the blue line is the line between the guessed location and the actual second location in the second image. And so it kind of uses this guessing procedure to actually match the stars. And this results in a full image of matched stars. And then from all of these stars, I can then calculate the centers, and all of these red circles here are all of the different centers calculated by the stars. And so this is really the main, this is the really good part about this algorithm, is that it proves that I'm definitely really close to the center of rotation. If I only use one star, how do I know if it's the right center? But if there's 40 star pairs in the image that all point at the same location, I know I'm pretty close. And so that was this algorithm here that calculates the center of an arc of stars is both used for the Mount's rotation every time I'm imaging, and also for the North Celestial Pole the one time I need to calculate it.
Sam, a question.
Yep.
That last image that you were showing, you have several, you have a bunch of solutions for the centroid. What's the sources of error for the centroid being located, not located in the same place? Is it the algorithm for the star selection, or the identification of the light source? What's the sources of error there?
Yeah, so the one main source is due to the fact that I'm basing the match stars. Right, no, that's not exactly it. I think it's mainly because of the centroiding algorithm and the noise in the image, and that it's never going to be a perfect location of that. And if the center points, the guesses, the red circles are the guesses, if they get super extreme, then it's because a matched star failed. And that was one thing I also tried to correct, was if these circles are way too spread out, then I knew that there was some error and that some of the matched stars weren't accurate. And there's also another algorithm I use to correct for matched star errors, but I think it's mainly due to noise and figuring out like the centroid being thrown off by noise.
And could it be also like the transparency of the sky, the level of seeing that we have through the air, the atmosphere?
Yeah, it could also be to the atmosphere issues, and also like maybe clouds and stuff all refracting the light and making it less accurate to the true position in the sky.
Cool, thanks.
Yeah. So I feel like another source of that I could improve upon was getting a better estimate for the center based on these averages, because like these are a lot more clustered to the bottom edge, and up top they're a bit more sporadic. So perhaps I needed more of a weighted average than just simply like clustering them all, just averaging. But in the end, I can run like 50 matched, like I can rerun it like using this guessed center point, the new average predicted center point. I can then try to rematch all the stars using that guess rather than the original guess. And I have to keep looping like that to get better matched stars and thus a better center point. What else? Is there another algorithm? I don't think so. So I think that's basically all of the improvements to the algorithms that I made this year.
Video should also play very well here. If you had it handy, don't go searching for it if you don't.
Yeah. Oh, I linked it, I think, in the sources.
When I was your age, plate solving meant taking the dirty dishes and getting them washed and put away.
Here it is. Found it.
And this is your video?
Yeah, this is video I made. Can you hear it okay?
Not yet. You have to play it through the computer in your file sharing setup.
Oh, okay. I guess I can read it out. So
That's
first
turned
you
off
must,
here.
yeah, wait, this is on YouTube. Can you hear the YouTube?
Yeah, in your share screen, there's a click play video and audio through the computer.
Um, what is it? Share sound, there it is.
The star in the first
Can you hear it
image.
now?
And star 2 corresponds to the
Got it.
same physical star. Algorithm work to determine a set of stars in multiple images that correspond to a single physical star in the sky, which allows us to determine the axis of rotation that the stars revolve around. So here on screen we have two labeled stars and a blue dot. For the matching algorithm to work, the user must first manually match a set of stars to a physical star. The algorithm will then use these stars to create a guess for the location of the axis of rotation that they revolve around. Star 1 corresponds to the star in the first image, and star 2 corresponds to the same physical star, but in the second image. We can recall that image 2 was taken many minutes after image 1, and during that time, that physical star has rotated around the real axis of rotation until it reached the position it is currently in, which is where star 2 appears now. There is also a star 3 that is not shown here from the third image, which was taken many minutes after the second image. This explanation only covers matching two stars, but the same principle can be applied to matching a third star. However, all three stars are required to develop a guess for the axis of rotation, which is shown in blue. Because star 1 and star 2 represent the same physical star at a different angle of rotation around the same axis, they both share the same radius from the axis. Therefore, we can draw two lines connecting the two stars to the axis. Both lines are the same length. We'll call this length R1. The next step is to determine how far angularly the stars have moved around the axis. To figure this out, we simply subtract the star 2's angle from star 1's angle, using the axis guess as a vertex. The result is an angle theta, representing the angle this star has traveled between the two images. In the sky, all stars appear stationary relative to each other. Based on this fact, we know that if one star revolves a certain angle about an axis in our camera frame, another nearby star will also revolve around the same axis the same amount. Therefore, we can apply our angle theta to another star from the first image to make a guess as to where that star moved to in the second image. On screen now is star A. This represents the location of a different physical star in the same first image as star 1. Let's draw a line, connecting it to the axis of rotation, and call this radius R2. Now, if we add the angle theta to the angle R2 makes with the horizontal, we can create a guess to the location that we think star B will be. Recall that star B is the location of the same physical star as star A, but in the second image. We also know that star B should share the same radius as star A from the axis of rotation, since they are the same physical star. As a result, our guess for the location of star B is here. The final step is to search a region around this guess for a star in the second image. In this example, star B happens to be right on our guess. However, depending on the accuracy of our guess for the axis of rotation, this will not always be the case. By adjusting the region we search around this guess for a star, we can eliminate false matches while getting good results.
Let me see it.
It's for every physical star.
I think that gives a pretty good explanation of star matching, the best I can do. I'm not sure if any of this is.
Sam, how long does the process take when you're doing a mapping of all these stars at once?
Like for the computer to process, or?
Yep, and for you to be totally polar aligned properly.
Okay. Currently it probably takes about 8 to 10 minutes. But my goal was to get this under 5 minutes so I could really be accurate. and really quick in getting into imaging. But the other part of it is bringing my laptop outside and setting up a chair for it to sit on and connecting the cables, which I hope to this summer actually move this program to a Raspberry Pi and have the Raspberry Pi hooked up to the tripod so I can just plug it right in and then bring out like my phone and move in or remote into the Raspberry Pi and actually do this all. Because the other thing is that like when I'm taking pictures of any object in the sky, I'm not just, or I have to take many images, like I take 3-minute exposures for 3 hours. And so I have to use an intervalometer. However, I didn't buy an intervalometer, so I programmed it and it runs on my laptop. So I have to leave my laptop outside for 3 hours, which I'm not really fond of. And so if I put that in the Raspberry Pi, then that'll be really good too. So
Excellent. That Fornax is a sweet mount too.
yeah, it's like they say you don't even need to use auto guiding. It's that's as good as it's going to get. If you put auto guiding, it's not really worth it. And your next step up is a celestial mount. So it's basically, these are my final 2 most prized images of Andromeda and Orion that I got. This Andromeda I got this spring, this fall, or this winter and spring, and Orion I got last January, I think.
Outstanding.
Pretty good.
Look nice.
And these weren't, this was like 3 hours of, no, I think Orion was actually like 30 minutes of exposures all stacked on top of each other. And Andromeda was like an hour, I think, but I'm always looking for better.
Sam, what's your location?
Currently I'm just outside of Danbury, Connecticut.
Is that
in
where these
Newtown.
pictures? That's where you took the pictures?
Yeah, both of these were from there, but actually this summer I'm moving up to New York, just north of Syracuse, about an hour north. And I have a lot darker of a sky up there for imaging. I think it's like Bortle 4 level. No, I think Bortle 2 or 3. And here it's like 4 or 5. So
Right, that's the high school you're with.
yeah, I'm in Newtown High School.
Newtown, okay.
Those are beautiful.
Thanks.
Yeah, really nice. Excellent.
Thank you.
So I attended a webinar sponsored by the AAVSO, the Variable Star Organization, where the scientist has a program that does photometry of the entire star field that's within an image. And a lot of the math that you use, Sam, is very, very much like the math that they used in order to do photometry. So you might be able to, go to the AAVSO, and they have a lot of documentation and programs out there that you might be able to leverage for moving forward.
Cool.
Very impressive. Does anybody got any questions for Sam? Except jaw dropping? Wow, Scott.
Well, Sam, what's next?
What's next? Definitely Raspberry Pi. That's first. Getting everything on the Raspberry Pi. Then probably attack plate solving. Perhaps if I can get plate solving running local on my main computer, I could have the Raspberry Pi connect directly to my computer, quickly run it, and then send it back. And then it's just actually getting out imaging, because basically all of these targets that I had, I went after the Whirlpool Galaxy. I think I went after Bode's Galaxy and the Cigar Galaxy. I went after the Eagle Nebula. I went after, there's another nebula right near that. And the Orion Nebula. Most of these were 1 or 2 times I even got out to do it, because I've constantly been trying to improve the program, get it all working. And so next is just to go out and image and try to get the best I can get.
And what was the optical end of this?
So for last year and the year before, it was a Nikon D500 with an 80 to 400 millimeter zoom lens. And then this past year, I got to use our newer camera, the Sony A7R4, which is 61 megapixels, and that was with a 600 millimeter lens.
Because everybody you see on the screen at one time or another, we've all had serious aperture fever. And it's just been amazing in the years that we've watched the evolution of imagery to see just how far it's gone. Are you, did you expect, as you began to formulate this project and think about what you were going to do, has there been any surprises? Has it brought to a point where you are glad to be? What's your own take on this?
I think the most fascinating part to me was exploring how many little rabbit holes there were. You have to figure out where the center of the star is. You have to get the noise out of it. You got to figure out how to gather the most light, but you don't want the aperture too open, or you can get some refracting issues or something. I think there was with the mount. The other thing was focusing. How do you focus on a star and get a perfect focus? And so I don't have it with me, but I hand cut out on a piece of paper how do you say, a Batonov mask that you put over the camera lens, and it has like 3 little lines that you line up. That was one thing I got to focus really good. So there's all these little rabbit holes that I think I really enjoy. But the main thing I was also excited to see was how good, like I always watch YouTube videos of people with like little telescopes with their like cool cameras, CCD cameras or whatever they are. And I was thinking, how close can I get with just a simple DSLR camera or a mirrorless camera that's made for daytime photography? How close can I get to those pictures with what I have? That was another thing that I really enjoyed.
Well, you've got a whole universe of opportunity with what you're doing there. That's great.
Yeah. What were you processing the stacked images with?
I think I used Deep Sky Stacker. And there's another one that I used when I was doing moon images, but mainly Deep Sky Stacker on my laptop.
Very familiar with it. Wow. And to go back to your barn door, the solution that people ended up doing was bending the threaded rod so that you had a curvature.
Yeah. And then you spin the little nut on it, or like the gear thing. Yeah, I couldn't get a gear or whatever. I don't know what the whole thought process was, but it was just, I'd rather be programming a polar alignment mount than trying to fiddle with this any longer.
Computer engineer, not the mechanical engineer.
Yeah, we didn't have any machines really. We just had chop saw for wood.
Wow. Scott, we should call for some applause.
Well, Sam, thank you very, very much. Yes.
Yeah,
Thank you.
All right.
absolutely. Thank you.
Thank you so much for sharing that with us.
Yeah, no problem. It's fun.
Well,
Well
this is your
deserved.
second science fair, right? You started this, we saw you last year and read the upstart of this project. Gee, it's too bad you don't have another year that you can.
Yeah, I don't get another science fair.
You're welcome
Maybe
to
in
keep
college.
touch. If you want any guinea pigs to beta test your inventions as you go along, give us a call. Yeah, we got some volunteers.
Definitely. I mean, the vision was to like send this program out and have it like free open source and let everyone use their own cameras for polar alignment. That was the vision, but I don't see when that will happen because I don't have enough experience with coding for all different camera makes. But definitely when I get more experienced, I'd love to attack that.
I've got at least 4 Raspberry Pis. I'm game.
Okay. Anybody else? Questions, comments?
I would just offer that there's device drivers that are fairly well defined within the astronomy community for most of the major camera makes, DSLRs and as well as the astronomy CCD cameras. So and it's an architecture that's shared so that you can take the device file and run it within the program without you have a translator within your program in order to be able to operate upon it.
Alpaca under Windows is the new one, and Indy for Linux.
So they like work with all cameras and they have like set functions to use for them?
The defined cameras, yeah.
Okay.
And actually, I learned so much on a website called Cloudy Nights.
Yeah, I've been there before.
Yeah, there's some smart people on there, and you can look up all the past stuff. But most importantly, you can ask questions, and you get a lot of help right there.
Yeah, that's cool.
Thank you, Sam.
Sam,
Yeah.
thank you very much. Good luck to you, although luck in your arena will be the cross-section of ability and opportunity. That's what luck
Yeah.
will be, and we hope you have a lot of that. So
Yeah, thank you.
thank you. Okay, we're going to move on, and Ishan is patiently waiting to share his achievement with us. Ishan is a senior graduating from Staples High School in Westport. And as soon as in our conversation, when you said Staples, I almost wanted to say, I'm not surprised. So many of our science fair contributors over the years have been from Staples High School. And so that was certainly noteworthy. And if I remember correctly, Sean, you're headed to Dartmouth next year up in New Hampshire, and you hope to be an astrophysicist. Well, you're already an astrophysicist, so what the heck? So I understand you had a love of physics probably before or as you entered high school. And of course, if you're going to go into physics, astronomy is if it's not a given, it's certainly a handshake throughout the whole journey. Ishan apparently learned from his peers that there was a really neat physics class that he ought to take. That the instructor, the professor, was capable, motivating, and very well liked. And he signed up for this course, which he took his junior year in high school. It's taught by Dr. Dick Morgan, who himself is an astrophysicist at MIT. So that's a pretty neat handshake between your classroom and MIT. That's what I was trying to establish in that last text. And he was Dr. Morgan was one of Ishan's advisors, and we were hoping he would kind of be able to listen in tonight. But well, all you guys are on really busy schedules, but we understand that. But Ishan's project title is Finding Gravitationally Lensed Quasars by Analyzing Polar Shapelet Decompositions. Now, I think most of us understand what gravitational lenses are and how they bring into focus otherwise unseeable objects due to the way their mass bends light around to create various patterns, rings or crosses or whatever. The challenge for you, Ishan, is the second part of that, the polar shapelet decompositions. And I think our brains will all be quite full after we peruse that with you. But you also, I hope, will make reference to the dark energy survey, which is a significant part of this. That had gotten by me somehow. So I got to stop talking now and say, please help me welcome Ishan Prasad to our meeting. All right.
All right, so I'll go ahead and share my presentation here. Let's see. Can you guys see this all right? Is this?
Yes, we can.
Yes.
Okay, cool. So, like Scott said, I'm Ishan Prasad, and my research project for the last about year and a half was on finding gravitationally lensed quasars by analyzing polar shapelet decompositions. All right. So my two mentors was Dr. Nick Morgan and Professor Paul L. Schechter. Both are associated with or working at the Kavli Institute at MIT. Dr. Nick Morgan is my physics teacher at Staples High School. So some stuff I'm going to be talking about during this presentation. I'll just give a quick overview and of gravitational lensing and the types of systems I'll be looking at and did look at during this research project. I'll also look at why lensed quasars are useful, why lensed quasars are difficult to find, and my approach to finding lensed quasars using polar shapelets and some of the results from my work. So gravitational lensing, specifically gravitationally lensed quasars, are really rare optical phenomena, and they're kind of optical mirages in space where light from a background quasar is bent by the gravitational potential of a really, really massive foreground object, usually galaxies like you can see here. And that creates an illusion where multiple duplicate images of the quasar are produced, and the systems we'll be looking at in this research project are quads or quadruply lensed quasars, where 4 images are produced like you can see here. So lensed quasars, specifically quads, are really rare and useful. Some reasons why they're rare is because of the alignment necessary for these phenomena to occur. So usually an alignment of a few arc seconds between the foreground galaxy and the lensed quasar, the quasar in the back and the observer, is necessary for this type of strong lensing to occur. And then within strong lensing, where multiple images or rings are created, double images are more common than these quads. So roughly 50 to 60 confirmed quads have been found in the last 4 decades worth of research. So it's very, very few compared to how many are out there supposedly, and the amount of work that's gone into that. So some reasons why lensed quasars and quads are useful are because they serve as optical laboratories in space. They provide insight into the size, the age, and the expansion rate of the universe. And that kind of tells us how the universe has evolved over time and how it will change in the future. It also just provides information on the distribution of matter, dark matter, in lensing galaxies and the universe as a whole, which are very important for these models of the universe. So lensed quasars are difficult to find, like I mentioned. Most searches use ground-based telescopes, and these images are pretty poor in quality compared to some of the more powerful telescopes like James Webb. For ground-based telescopes, the images can be described using the words grainy, pixelated, fuzzy, for the most part. And at these low resolutions, quadruply lensed quasars look very, very similar to elliptical galaxies, as you can see here. So the center image is a ground-based telescope image of the lensed quasar system HE0230. The left image is an image of the same system using a more powerful telescope. And as you can see, there are 4 distinct kind of parts to this image, which indicate that it is in fact a lensed quasar. But if you go look back at the center image, it looks very, very similar to what an elliptical galaxy would look like in black and white. So that causes a lot of difficulty for astronomers in finding these systems, on top of the fact that they're intrinsically rare, just due to the alignments. So also, by the way, if you guys have any questions, feel free to just stop me and ask them. So next, I'll talk about some past and current techniques for finding these. There have been many serendipitous discoveries of just looking through surveys and spotting some large separation systems like the famous PG 1115 system, which is in this image down below. It was one of the first lensed quasars found. You can also visually inspect images, which are mostly limited to high separation systems, 1.5 arc seconds or above. And that's just because there's enough separation where you can tell four distinct components to the image. And that's mostly what my research advisor did in his work back in the early 2000s and in the 90s as well. So more recently, with advanced technology, machine learning algorithms have been developed to kind of sort these images from large databases like the dark energy surveys, the Sloan digital sky surveys. But there's still no reliable way to find small separation systems. So many of these small separation systems are yet to be found, hidden within these large surveys like I mentioned before. So the goal of my research is to find a way to distinguish low separation quads from elliptical galaxies. So my approach was using polar shapelets, which are very, very complex shapes that I don't think I even understand fully yet, even after studying these extensively for the majority of my project. But some things we do know is that they're an orthonormal set of basis functions, which are derived from the equation in the bottom right here. There, if you can see, there's it's kind of a modified associated Laguerre polynomial, and those are equations usually found in quantum mechanics. So that's kind of where this function comes from. And the first few polar shapelets are in this graph to the right. They can be, each shapelet is described by their unique N and M values. So there's a NM value 1,1 shapelet, which is this kind of just white blob over here. There's the 1,1 shapelet, which has the dark side on the left, bright side on the right, and so on for the first six NM shapelets. As you notice, some shapelets have imaginary components, and by weighting imaginary components of shapelets to the real components of shapelets, you can actually rotate them, which allows you to model more images, more galaxies, more quads, which makes image analysis more intuitive and easier, which is why we use these special shapes in the first place. Some also important properties, while they aren't vectors, polar shapelets have vector-like properties. So to use these shapelets, you can actually decompose them in any astronomy image into these shapelets and see which ones are being used and how much of each one are being used, and use that to kind of analyze images and find patterns in kind of the contributions for lensed quasars versus contributions for just normal elliptical galaxies. So this decomposition process can be done using a dot product of sorts, where you multiply the pixel values for the shapelet and the pixel values of the image of a galaxy, for example, and then adding all of that up, all of those multiplied pixel values. And that creates the strength or weighting of that shapelet that's being used. So I did that for the first 6 polar shapelets, and that was sufficient to kind of distinguish these two systems, as I'll describe later. So you can actually reconstruct astronomy images using these polar shapelets to model them, and it can be done using a linear combination of polar shapelets. So the coefficient, or the weighting of a shapelet times its shapelet plus the weighting of another shapelet times that shapelet, and so on, can be used to model pretty much any astronomy image you want. So that's very, very useful kind of math going on there. So to actually do the research, I deconstructed 10,000 images from the dark energy survey and 2,000 synthetically generated quads from the Uguri-Marshall lens catalog. Uguri and Marshall were two astronomers who decided to create this catalog to further study on these rare systems. So after deconstructing them, I had plots, which I'll show in the next slide. And over those plots, I superimposed a grid to help quantify the probability that an image is a lensed quasar rather than a elliptical galaxy. And I found that probability using an odds ratio approach, which I will describe in just a second. So the two equations I used for analysis was finding the odds ratio, which is the percentage of lenses in a square divided by the total number of lenses, so that would be 2,000, divided by the number of DES images or galaxies in that portion of the plot, divided by the total number of DES images, or 10,000. And from that, I found the probability by dividing the odds ratio divided by the odds ratio plus 1. So I will show you those plots in a second, but I wanted to first show you my actual decomposition. Here's an example of one of them. So here, on the leftmost panel is the original image of the DS galaxy. The next one on the right is my reconstruction of the galaxy. So as you can see, there's it's able to model the galaxies quite well. It's able to capture a bulge on the left here and on the top here, and kind of model the asymmetries of the natural galaxy. And then there's the residual and the components of the shapelets being used. So now I'm going to show you the plots. So on the bottom left here are all of the 6 shapelets I used, and their contributions in lenses versus galaxies. So the lenses are in blue. So for the 0, versus 1, shapelets, here's kind of where they land on the plot versus the galaxies, which are in this portion of the plot, and so on. Here's I'm comparing the 0, shapelets versus the 2, 0. Here I'm comparing 0, versus 2, 2. And that kind of, those comparisons kind of help me see which ones are being used for lenses versus galaxies. And the plot on the bottom right are the probabilities after conducting the odds ratio that I described earlier. You can see the superimposed grid. And then within each part of the grid, there's the probability. Next component of my results are the rotation angles. I wanted to see if certain shapelets are being rotated more for lenses than galaxies, but it seems like there wasn't any difference between those two, which is very interesting. So next, I was able to use those probabilities. Use those probabilities from this kind of grid right here to rank my top 10 candidates, which are listed here. I wanted to show you guys what my top candidate is for the DES survey that I looked at. And this is DES J0301, which, as you can see, there are definitely asymmetries. There's kind of a bulge down in the bottom left here. There's some kind of stretching and kind of asymmetries in the top part and the right part, which is very, very characteristic of lensed quasars, right? We expect those kind of asymmetries around the edges of the systems.
I'm frozen.
Wait, sorry. Okay.
Speaker is not frozen, if that's what you're asking.
All right. Is everything working? All right. Can you
Yes.
still hear me? Okay. So seeing this candidate of our top candidate, we can see that our algorithm is definitely working. It's able to kind of pick out the most asymmetric and the most kind of quad-like systems from this survey of 10,000 systems. So it's definitely very promising, and it means that this work has been a success. So some conclusions in future work, like I mentioned, we've successfully found a way to sort images quickly to find those with those systems with quad-like properties. The next step is to apply it to a larger data set and kind of find more candidates and kind of confirm these using more powerful telescopes like the James Webb. One thing I'd like to say, though, is that this algorithm isn't perfect by any means. It's only analyzing structure of the systems, and they're kind of a series of checks that need to be done in order to confirm that a system is in fact a lensed quasar and not an elliptical galaxy. And one of those is by checking the filters. So most galaxies produce kind of more bluish light compared to quasars. So quasars, kind of their structures hold in different bands, namely the red filters. So by checking and comparing the blue filters and the red filters, I'm able to do another check and see if structure holds, in which case it would be a lensed quasar. For elliptical galaxies, its structure would kind of change and shift and kind of melt away in sorts for the red bands, because less light is being produced compared to lensed quasars. So thank you. That's the end of my presentation. If you have any questions, feel free to ask them.
I have one minor one, and that was only because I'd never heard of it before. When you talked about the dark energy survey, you said the OM catalog as well. I missed what the O stood for. The M I got was Marshall.
So the O stands for Oguri. I believe he's an astronomer doing research in Japan with various institutes over there.
Able to spell it at all?
Oguri is Oguri.
Thank you.
Mm-hmm. And they released a paper with the survey in 2010.
Ishan, has this pursuit by you and others in this way, could you say anything about contributions it's making to the dark energy conversation?
Yeah, no, this is definitely a huge contribution to astronomers who are looking at these surveys like the dark energy survey. It indicates that a lot of smaller separation systems have yet to be found, and it kind of keeps the door open to this kind of exploration, this quest to find gravitationally lensed quasars, and keeps the DES in kind of keeps it in the research being done. So hopefully, after applying it to my algorithm to a larger subset of the DES, I'll find some more candidates, hopefully find an actual lensed quasar, and that will kind of bolster the research being done on this particular survey.
Thank you.
Mhm.
John, can
It's
you
not-
go back? I'm sorry. Can you
go
go
ahead,
back
Chris.
to the photo that you had of the lens quasar a couple pages back?
Yeah.
Yeah. Yeah. Go
Would I
for
pass?
yeah, go forward.
Okay. This
There you
one?
go.
Okay, cool.
Is that a known lensed quasar there?
That's not yet.
That's one you discovered using
That's
this?
one I've discovered. Yeah.
Okay. Now, how would you differentiate that as a lens quasar from something like a colliding galaxy? Two colliding galaxies.
The first thing that stuck out to me were its asymmetries. So for these low separation systems, you can't definitively say that this is a quad versus colliding galaxies or elliptical galaxies. That's kind of one of the main issues that this project is trying to tackle, is kind of find the most likely candidates for further investigations. So
Okay.
what makes me think that this is a pretty strong candidate are the asymmetries in the bottom left, in the top, and the right here.
Okay.
Those are less common for colliding galaxies.
Okay. Wow.
So my question was kind of related to that too. Were you able to take any of these candidates to the next level by looking at other sensors, like imaging done by Hubble or any of the previous, like Spitzer or something like that?
No, I unfortunately haven't been able to check them using more powerful telescopes yet. I'm hoping that that's one of the goals for the summer, is to first apply it to a larger data set, so that we can find even more likely candidates. That should take about, I'd say, like a week at most, to just run through 1 million images. I've gotten it down, the algorithm down to around 5 seconds per image. So that's certainly one of the fastest algorithms out there. And after I apply it to 1 million data sets, 1 million images, we will be ready to send it back to MIT, and they'll take over the rest.
So the other question that I had is, did you run your algorithm against some known quasars?
Yes, yeah, we did actually, and those did in fact come to the top of the pile. Those were I actually did it to initially check whether my algorithm was working or not, was by kind of mixing the two catalogs of the OM catalog and the DES catalog, and I threw in some other images like the PG 1115, and kind of saw relative to the lenses how it's filtering out. And most of the lenses came to the top. More of the lower separation systems, where it's harder to find, did kind of sink to the middle of the pack, but it did a good job of separating those and confirming that it was able to pick out the lenses.
So, yeah, I think that would be a correlation factor or some other measure that validates the procedure. I think is a really nice kind of footnote on anything that you present, going forward.
Yeah.
And do you know if this works on all of the quad morphologies, or does it work better on certain kinds?
It works on all of the main configurations. So we actually, sorry, okay, I just passed it. We actually looked at all of these types of systems, kind of like this cat's paw configuration, the Einstein cross. We actually looked at all of these, and it does in fact work for all of those. Systems where there's kind of more like smearing, kind of like these, it doesn't work quite as well, but it works surprisingly well for lower separation systems with the same configurations.
Well, this is fascinating stuff, and I can, if you can, direct the sensors, more expensive experiments to better candidates, I think this will pay dividends in a big way.
Mm-hmm. Definitely, yeah.
Ishan, with these images up here,
Mm-hmm.
Are we seeing in most of these the quasar, such as at the center of the Einstein cross?
I believe for all of these, this kind of, wait, can you see my mouse? Or you can, okay. See, yeah, that kind of faint blue dot in the middle of the
Yes.
the cat's paw and the Einstein's ring, that's actually the lensing galaxy. So the kind of the duplicate images of the quasar are kind of spread out around the outside.
Well, I'm sorry, that's the galaxy that we're seeing. Yes.
Yeah, so in the middle is the galaxy, and the
Yeah.
Yeah.
Thank
Gotcha.
you.
Mm-hmm.
Anyone else? Oh boy, that was an excellent presentation.
Thank you.
I have to report out that my brain is full.
Yes.
Sorry about that. Yeah.
Geez. So you're going to be diving right into this at Dartmouth, and that should be so exciting for you.
Yes. No, I'm excited because right now I'm not very good at some of the astrophotography. I have trouble with the kind of the light pollution in my area, at least, because we're pretty close to New York. So up in New Hampshire, it will be a lot better for that. So
Yes, it will.
yeah, I'm looking forward to it.
So
Even
well,
now,
okay. Go ahead, John.
nope, nothing.
Okay. Well, thanks again, and you're certainly welcome to drop by, and we'd love to have you present something here in the future, but that would be a real reach to have that kind of scheduling come together. But you're a member of the club. You and Sam are club members, and you're certainly welcome to drop in any way you can find how to. And I'll get the magazine subscriptions started. I've fallen a little behind in that, and we should be good. Enjoy. And we hope to see your images in those magazines.
Yeah. Yeah. All right, Ishan and Sam, thank you, both of you, for your presentations. Those were terrific to end our year on. And Scott and Bill, both you guys, thank you for your work on this.